Time travel has long captivated human imagination, inspiring countless stories and theories. But beyond science fiction, the question remains, is time travel possible within the laws of physics? Exploring this involves delving into theoretical physics, understanding potential paradoxes, and examining how time operates differently across the universe. Albert Einstein's theories of relativity provide a foundation for understanding time travel. According to his special theory of relativity, time is relative and can vary for observers in different frames of reference. This means that time doesn't pass at the same rate for everyone. For instance, a person traveling at speeds close to the speed of light would experience time more slowly than someone at rest. This phenomenon, known as time dilation, implies that traveling into the future is theoretically possible. Astronauts aboard the International Space Station, moving at high velocities relative to Earth, age slightly less than those on the planet, effectively becoming time travelers to the future, albeit by fractions of a second. Einstein's general theory of relativity further expands on this by introducing the concept that gravity affects time. Time passes more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This has been confirmed through experiments comparing clocks on Earth's surface with those on satellites. The latter tick faster due to weaker gravitational pull. While these effects are minuscule, they demonstrate that time travel into the future aligns with our current understanding of physics. Traveling to the past, however, presents more significant challenges. One theoretical proposition involves wormholes, hypothetical tunnels connecting separate points in space-time. If such structures exist and could be stabilized, a monumental if, they might allow for backward time travel. However, the energy requirements and potential instabilities make this concept highly speculative. Time travel, especially to the past, introduces paradoxes that challenge our understanding of causality. One classic example is the grandfather paradox, where a time traveler goes back and inadvertently prevents their grandfather from meeting their grandmother, thereby preventing the traveler's own existence. This creates a logical inconsistency. If the traveler doesn't exist, how could they have traveled back in time to alter the past? Another intriguing scenario is the bootstrap paradox, where an object or information is sent back in time and becomes the very catalyst for its existence in the future, creating a loop with no clear origin. For instance, a scientist receives a blueprint for a time machine from their future self and builds it, only to later send the same blueprint back to their past self. This raises questions about the origin of the information and challenges our notions of cause and effect. Beyond these, there is also the predestination paradox, where events are seemingly fixed in time despite efforts to change them. If someone travels back to prevent an event, their actions may be the very cause of that event occurring. This idea suggests that time might be self-correcting, ensuring that any changes still lead to the same outcome. Another lesser-known paradox is the Polchinski's paradox, which involves a hypothetical billiard ball entering a wormhole and emerging from the other end in the past, potentially colliding with its earlier self in a way that prevents it from entering the wormhole in the first place. This paradox questions the consistency of time loops and whether physical laws would allow them. Time is not an absolute universal constant but rather a dimension intertwined with space, forming the fabric of space-time. This means that time can flow differently depending on factors like velocity and gravitational strength. For example, time passes more slowly on massive celestial bodies due to their strong gravitational fields compared to regions with weaker gravity. This concept is crucial for the accuracy of technologies like GPS, which must account for time dilation effects to provide precise location data. Furthermore, the twin paradox illustrates time's variability. One twin travels at near light speed on a space journey while the other remains on Earth. Upon returning, the traveling twin would be younger than their Earth-bound sibling due to experiencing time more slowly during the high-speed journey. This thought experiment underscores how time is experienced differently based on one's motion and gravitational context. The scientific community holds diverse perspectives on the feasibility of time travel. Some physicists argue that while time dilation allows for forward time travel, backward time travel remains implausible due to the paradoxes and the requirement for exotic matter with negative energy density to stabilize wormholes. Others explore the possibility of closed time-like curves, solutions to Einstein's field equations that permit paths returning to the same point in spacetime, theoretically allowing for time loops. However, these concepts often lead to paradoxes and require conditions not yet observed in our universe. Some theories propose that altering the past could result in the creation of parallel universes or alternate timelines, thereby avoiding paradoxes. In this framework, any changes made by a time traveler would spawn a new branch of reality, leaving the original timeline unaffected. While intriguing, these ideas remain speculative and lack empirical support. Time travel continues to straddle the line between scientific possibility and imaginative speculation. While traveling into the future aligns with our current understanding of physics, journeying to the past presents significant theoretical and practical challenges, not least due to the paradoxes it introduces. As our comprehension of the universe deepens, the enigma of time travel persists, inviting both scientific inquiry and philosophical contemplation.